My name is Pavan Idara. I am a software engineer at Google. Today I'll talk about how Google is bringing the power of BigQuery to Apache Iceberg. So this is a customary BigQuery architecture slide that we present everywhere. So BigQuery is built on the principle of decoupling of storage and compute. A high bandwidth, full bisection bandwidth network, petabit scale network connects a highly replicated, durable storage system to the highly available compute cluster. A compute cluster is distributed across many nodes in a region. One of the defining features of BigQuery is it's a disaggregated shuffle layer, shuffle is the exchange operator. Operators in a query plan exchange data via disaggregated memory, distributed memory file system. This gives the engine the scalability and flexibility. BigQuery has cloud scale streaming ingest, hundreds of gigabytes per second to terabytes per second of streaming ingest, and of course bulk load. And it's standard compliant SQL and client libraries in many languages allow it to be embedded in various places into the ecosystem. So I'll talk a little bit about BigQuery's journey with Iceberg so far, and I'll talk about what is coming up in the next few months and years. So BigQuery started with what are called native tables. BigQuery's native tables are store data in a distributed file system called Colossus, and they use a storage format called capacitor. Capacitor is the successor of column IO. Column IO, is basically one of the things that inspired the open source SparkML. BigQuery's storage engine has highly scalable metadata and real-time infrastructure that give it the performance and scale. So we started our journey with Iceberg over the last few years with self-managed Iceberg support, with in-situ querying of data in cloud object stores, S3 and GCS, Google Cloud Storage. We were in this mode. BigQuery allows read-only queries over the Iceberg data. Some of the foundational pieces of scalable metadata power this querying of this Iceberg data. Recently, we have added support for fully managed Iceberg tables. So we are bringing the full capabilities of the BigQuery engine with the openness of Iceberg data, so that you can actually get all the management of BigQuery tables on your Iceberg data in your own cloud storage buckets. So I'll talk about how we are doing this over the next few slides. So Apache Iceberg Lakehouse. So we are trying to build an Apache Iceberg Lakehouse on Google's infrastructure. So there are some fundamental pieces on which we are building it. So we have rich scalable metadata management system for petabyte scale datasets. We have many petabyte scale datasets in our that we have experience with our storage system. Our metadata management, unlike other places that you might see, is deeply integrated into the query engine. So there is the format, and then there is how you access the format. And metadata is a key component of it, as you have probably seen in many talks today. So metadata management, we deeply embed metadata management into the query engine, which is how we extract a lot of performance. So this embedding of metadata management also enables various objects, auxiliary structures like materialized views, search indices, etc. over these Iceberg tables. For example, if you have materialized views and if you want to do what is called smart tuning or automatic view selection, you want to rank the views. So our highly scalable metadata management system allows you to rank the views at the time of querying in order to select the best view for the query. So in summary, we'll bring the complete feature set of BigQuery tables to Iceberg with full interoperability between various table types. So I want to present a few components of our Lakehouse vision that we are building on right now. So we are building an Iceberg spec compatible REST catalog that will be available sometime in summer. We are allowing through this Iceberg catalog direct access to Iceberg data on GCS for various OSS engines. You'll see a demo of that later in this talk. So we want to allow seamless access to Iceberg both for read and write from multiple engines and querying from multiple engines. In addition to that, we want to bring some modern Lakehouse capabilities on BigQuery for your Iceberg tables through its differentiated infrastructure that Google has. So I'll talk about what this modern differentiation I'm referring to is, just a few components of it. We want to bring industry-leading real-time ingestion with BigQuery high-throughput streaming API. So often when people talk about streaming, they talk about append-only datasets, append-only logs. Not just append-only logs, we also want to support high-throughput streaming mutations. For example, these are very common in scenarios where you want to replicate your operational stores into Iceberg tables. I'll have a demo of that later to drive home that point. So we want to bring the power of full SQL with transactions, multi-table transactions, and fine-grained mutations to reduce write amplification in a highly scalable way over your petabyte scale datasets. And finally, we want to bring continuous SQL queries for real-time analytics to your Iceberg data. These are things that we are actively working on. Some of these you'll see. I'll present a demo of it in a second. So in this short talk, I'll talk about two technical pieces of our architecture that define BigQuery's support for Iceberg. So the first one is the real-time ingestion architecture. So this is typical of other systems, but we have some special features here. The BigQuery storage write API, the box that you see at the top, is the entry point for the streaming into a BigQuery table. The storage write API is a gRPC API, for high throughput streaming. The abstraction with which the client works is called a stream. Essentially, I think of a stream as a pipe into a table, and you create on your Iceberg table, you create a stream and you start streaming data through that stream. Like you can stream at hundreds of gigabytes per second into your tables through this. The heavy lifting of the data is done by what is called the stream server, the boxes at the bottom, that are built on top of a distributed storage called Colossus. The stream server is responsible for the logging layer and the recovery protocols. As the data is written, few things happen. There is a storage optimization service that reads at the head of the table, at the head of the streams, and continuously does a few things. It first continuously range partitions the data in real time. So this is necessary for any performant queries on your data. So there is high throughput ingestion. And in this case, we don't force the user to perform any partitioning. All partitioning is done by BigQuery after you ingest. Unlike other systems where you have to partition upfront and write to your Iceberg tables, in our case, we leave the heavy lifting of partitioning to the back end of the system. The storage optimization service performs real-time partitioning and in the meantime also converts the data into your Iceberg format on GCS. And since the ingested data is in write optimized format and the read optimized store is the Iceberg data, if any query or any read operation arrives in the meantime, BigQuery will automatically stitch the read and write optimized store to get a strong read after write consistency for your data. The BigQuery read API allows other engines outside BigQuery also to get the same strong read after write consistency. So that was this little bit of the storage piece. For people who are like the query processing enthusiasts, I talk a little bit about metadata, how we manage metadata in query processing, just to give a glimpse of where the scalability comes from. So imagine this typical sales table in a data warehouse. It is partitioned by the order timestamp and it's clustered by customer key. Could be clustered by anything, but let's say it's the customer ID. So we define a shadow table on this, which is the index of the metadata of the table. And the metadata of the table uses this following generic type for each column. So each column's metadata is expressed as this extensible generic type, which has a number of properties about the column. So for each block is an abstract notion of a set of rows. For simplicity, think of it as an Iceberg file, Parquet file on cloud storage. So for each file, for each column, we maintain all this type, generic type describes the metadata that is stored. So you can see a variety of metadata here. You can see min-max values, which are the common ones. You can see dictionaries. You can see Bloom filters. And for advanced types like geography, we also store the S2 covering. Ryan spoke about this in the talk earlier today. BigQuery already has a geography type, and we store the S2 covering, which is a bounding box metadata, in order to do block pruning. Armed with this generic type, we define this shadow table called CMeta, stand for columnar metadata, on the sales table. So it has a few columns. I'll just go through it very quickly. It has the block locator column. Think of it as the file, path to the file in object store, GCS. And it has two other columns, the creation and deletion timestamp, which is basically the birth and death timestamp of this particular block. There is a bitmap on this for fine-grained mutations that is not expressed here, but that gets past side channel. But I mean, imagine that that is also part of this table type. Additionally, for each column in here, in this base table, for example, the order timestamp column has a struct column which is defined by that generic type. So each column gets its own type. And this index itself is clustered for seek optimized access, so that you can get to your blocks very quickly. So given the base table and the index, now let's look at how this query is executed. So this query is a simple query that's calculating the sum over a small period. So the query optimizer essentially rewrites the query into something, into its algebraized form, into a which is equivalent to a query something that looks something like this. So this is the original query itself. And then there is an additional predicate that is added. Basically, it's looking for, there is a virtual column in every table called the block locator. It looks for that block locator inside the index, and looking for the blocks that would match, that may contain the data that match the original predicate. So this is there could be false positives here, but there are never false negatives. That's the requirement. So it's looking for the blocks from the index, and it's saying this bottom part of the predicate is for snapshot isolation. Only look for the blocks that were alive at the time this query ran. And it's also saying, given the input predicate, we came up with a derived predicate on the index itself. I chose a simple example of a predicate here, but just for simplicity of explanation, but you can think of arbitrary predicates. For example, you can have a function on order timestamp which deals with time zone and so on, which uses time zone of the timestamp and so on. And what we will do is to generate a derived predicate. We call it a falsifiable predicate, which essentially uses the properties of the functions that you used on the original predicate, monotonicity, etc., in order to determine what would be the derived predicate that should be applied on the index. So the query, in reality, the query is executed as follows. So if you look at the right side of that, it is executed as a semi-join between the base table on the left and the index scan on the right. The index scan could be a seek, but in this case, like the query plan shows a scan. So we scan the index on the right side. We scan the index on the right side and apply the filter, and the blocks that match go into this union, which is essentially a shuffle. And if there is only one file, it's easy because you can just say that file can be transferred to this side. But if often it's a large number of files, if you have a query that has a very non-selective predicate, and those files are stored in an intermediate shuffle, just like data from between query plan is exchanged between query plan stages. So that's the high-level summary of how a query is executed with our scalable index. So I'll do a couple of live demos just to show how BigQuery is accelerating Iceberg support. How do I get rid of this? Okay, so our first demo is one of ETL. ETL is a common operation from an operational store to a data warehouse. So in this ETL, we'll perform an ETL into a target table, into a target Iceberg table. The target table is a table that is inspired by the TPCDS catalog sales table. It is about 2 terabytes in size, and its data is stored in this GCS bucket at this location. I'll show this location in a second. The other part of the ETL operation uses a staging table, which is in.
Can you zoom into the
Good. I can't really work here with that, but okay, let me. Okay, thank you. So the source table of this ETL operation is the staging table is a BigQuery native table, which has about 44 million rows. It's a table stored in BigQuery, but it could as well have been an Iceberg table. I'll show that in subsequent demos. I just chose 2 different table types to show the interoperability. So the data is stored in this GCS location. As you can see, the sales target table is here. It has the data and metadata folders, and the metadata JSON corresponds to the time at which I created the table. Now let's go back to the query, and you can see that it has the table itself has about 70 billion records, the target table. So what we'll do is the typical ETL operation takes a staging table and reconciles the staging table into a target table. So let's first look at the staging or source table, what it contains. So the staging table contains 10 days worth of data from 0105 to 0114, and it has about 4.5 million records per day. This is the total. This is the roll-up of the number of records. It has about 4.5 million records per day, and almost all of the orders have shipped. Essentially, the ship date column in each of these orders is set to a value. A very, very small fraction, as you can see here, is not set. Now let's look at the target table to see what it contains. Oops. So the target table, I'm only querying for that interesting date range that the source table contains, just to limit the range of the query. So it contains data for 0105 to 0111, even though I queried for up to 0114. Essentially 12, 13, and 14 dates are not present in this table. And as you can see, none of the orders have shipped. All the 4.5 million orders per day are not in shipped state. Now let me run this merge DML statement, which merges the state of the source table into the target table. So essentially, a merge DML statement is a poor man's transaction, so to speak. It basically allows you to do update, delete, and insert in a single statement. And later you'll see a demo with a multi-statement transaction also. But what this is trying to do is it's trying to match the target table rows with the source table on the order keys, order number and item code. And it's saying when there is a match, set the ship date from the source table into the target table. Essentially mark the item as shipped when there is a match and the item state is shipped in the source table. And if there is no match and the source table has a net new order, copy that into the target table. So as you can see, it affected 44 million rows. If you remember, that is the same number of rows we had in the staging table that was over here. So finally, let's look at whether the merge did what we actually expected it to do. We should see 10 days worth of data now. So as you can see, days 12, 13, and 14 got added to the target table now, and all the orders for the remaining dates have been marked as shipped. Before I end this particular demo, let me show the interoperability of this across engines from a Spark notebook, what happened here? So let me try to do this from a different Spark notebook. I planned for redundancy. So let me run this. Anyway, so let me go look at the Iceberg table to show that we actually reflected the state of our merge into this. As you can see here, this one just ran just now a few minutes ago. This was the result. The second metadata JSON file, which was produced at 2:18 p.m. was a result of the merge that we just ran. Okay, this is alive, so I can run it here. also. So what we expect to see is yes. As you can see here, we are seeing all the rows from 0105 to 0114 and for across all the dates, and this is exactly the same result that you saw in BigQuery. This shows the interoperability of the Iceberg support across multiple engines. Date writes that were done in BigQuery are now visible to any other engine. So I have one other demo showing a couple of modern capabilities of these Iceberg tables that we are bringing from BigQuery. So this is another table. This is a different Iceberg table which has the same 70 billion rows, and it's also similar to the previous target table that you saw, and its data is stored in Iceberg as well, in Iceberg format in this GCS location. This time I'll again perform an ETL operation, but this time I'll do it using a multi-table transaction. And the two tables, the first one is this target table, and this one is the staging table. This one, in this case, I've chosen both tables as Iceberg. So we'll look at a multi-table transaction that commits the changes from one table to the other and atomically modifies both of them. Before I do that, let me show you the state of the two tables. So this is the source table. The source table has 450,000 rows, and again most of the orders in this table are shipped. A very small fraction are unshipped. So it has data for just one day. It's just an example. And this is my target table, which has data for several days, but I just picked that one day just to show what it contains before and after. So this has 4.5 million orders. All of them are in unshipped state. Now let's run a multi-table transaction. And the interesting piece of this multi-table transaction is that it's doing a fine-grained mutations. It's doing row-level mutations on BigQuery table, on Iceberg tables, to avoid any write amplification. So if only one row in a file is touched, we only want to update the one row and not rewrite the entire file. So while this DML is running, as you can see, the DML, the statement, the transaction finished. The merge statement modified 450,000 rows. If you remember, this was the number of rows in the staging table. And also, it atomically deleted the 450,000 rows from the source table. This is the concept of using a transaction between a source and staging table is quite useful, because you want to perform idempotent operations. If the copy into the source table, target table succeeded and the source table did not get truncated, you might do duplicate mutations on your data warehouse. So as you can see, we can achieve a consistent and atomic operation across these two tables using this transaction. So let me finally show that the two tables did get actually mutated. So this is the target table, and for that same day, you can see that out of the 4.5 million records, 450,000 are now shipped, and the remaining remain unshipped, because this is the only set of orders that were marked shipped in the source table. We should also expect to now see the source table is empty, because we truncated it using the delete statement. No rows in the source table. So the final thing I'll show is transaction is actually performing these operations in real-time manner. So you can do so as I said earlier, streaming is not just about inserts. We want to perform mutations in a real-time manner, essentially allowing you to replicate your data operation stored to your Iceberg Lakehouse. So in order to do that, I just picked these 3 rows as an example to show their state, and later I'll make some changes using the streaming API and show that the changes get reflected in real time. So there are 3 rows in this table, the 3 rows, and our goal is to delete this row, this one, and mark the other 2 rows, change the quantities to 200 and 400. So that's our goal. In order to do that, I will use the BigQuery high-throughput streaming API to perform mutations on this table. So the BigQuery high-throughput streaming API, which was the real-time streaming architecture diagram that I showed, allows you to send mutations as individual rows into the table. You can run these mutations at very high throughput into the table. So there are three rows, and the change type delete, change type upsert, and change type upsert, and we want to apply these changes. So very quickly, let me stream those changes into the table. So what it is doing is it's marking this row as deleted. The other two rows is changing their quantity to 200 and 400. And one last interesting column is this change sequence number. You can think of it as equivalent to the log sequence number in traditional databases like MySQL. Essentially, allowing the external system to specify it allows it to dictate the order in which the changes are applied. This is very useful for when multiple threads or multiple processes are streaming in a distributed environment. That is how you get scalability for your mutations. Finally, let me just show that this was not, this actually did what it expected to do. So as you can see, it deleted this one and applied the two changes of quantities in near real times. This way you can stream your operational store into your Iceberg Lakehouse at very high throughput. Thank you. That's all I had.
Right.